Welcome, everyone, to what is our first ever podcast, our first flight or maiden voyage, whatever you might want to call it. Today's episode is titled, So I Need a Flow Meter. And this is for folks that want to understand, first of all, what a flow meter is, where it is used, and most importantly, how to select a flow meter for your specific application. My name is Scott Lawson. I'm joined today by two experts in the field, each with broad industry experience. We plan on looking at this from really at what I would say is two different viewpoints. First, of course, in the title, I need a flow meter. What's next? And then look at it from the side of things as, hey, I have a problem. Does a flow meter help me solve this particular problem? So again, my guests today are Dane Etwaroo, a technical sales specialist in our measurement instrumentation business unit here at Spartan Controls, and Morgan Rodwell, Senior Director of Process Technology with Fluor Canada here in Calgary. Gentlemen, thank you very much for joining me today. Dane, would you be able to just tell us a little bit more about yourself?
Yeah, for sure. Thanks, Scott. I really like that maiden voyage or into the unknown, because I feel we're going to really crank it off today. So have some patience with us. I guarantee we'll only get better as we go, but we'd love feedback. In terms of my background, I'm an electrical engineer, and I've been involved with Spartan for going on 13 years now. I've got some background in gas processing, combustion, some compression, and now on the measurement instrumentation side. So a lot of flow, pressure, temperature, level, and water cut. And we'll kind of dive in today. Morgan, I'll let you take it off.
Thanks, Dane. Yeah, I'm Morgan Rodwell, and I've been with Fluor for over 25 years, and in the industry a little bit longer than that. And I've done everything from very conceptual engineering through detailed design on things from gas plants and gas processing through oil refining and upgrading, SAGD heavy oil production, and even into some strange stuff like nylon yarn spinning. So I've got a vast experience. I'm also a big proponent of making sure that you solve the real problem you're looking for and looking at, not solving the wrong problem with the wrong tool.
Perfect. So suffice to say that you guys know a good deal about the topic of today, which is good because admittedly I do not. My background is in DCS, and it's not to say that I haven't worked with or interacted with different varieties of flow meters before, but it was always from that perspective, from a programming and configuration side of things, or making sure it was displayed appropriately for an operator at a plant on the HMI. So I take the sort of side of things that I'm the newbie, the layman today. So I don't want to assume that all the folks that are going to tune into this are going to know right off the bat. I'm sure most have maybe heard of a flow meter, but not necessarily the different types and sort of what's different about some of those and where they fit and why. So yeah, that's kind of my take on today's discussion for sure. So I kind of wanted to introduce this a little bit and ask you guys if you know a little bit about the history of flow metering. I did a little bit of research on the weekend and was able to find out a little bit, so I just wanted to throw it out there. So first, where folks wanted to try and actually meter the flow of a particular moving liquid was actually in ancient Egypt, if you didn't know that. Going back to actually trying to, basically they were looking at sort of different canals and the flow from each different canal, and they knew apparently the particular volume of one canal to the next, and they were actually doing this to try and sort of monitor crop irrigation and the different, how much water was actually available.
So Scott, I'm going to interrupt you here. You've gotten like 10 brownie points for diving back to ancient Egypt. I did not think we were starting there, but yeah, you're definitely above a layman now.
Yeah. I was waiting for Bernoulli to come up, and he went way earlier than that.
He went back to fundamentals. That's great.
That was kind of the next. I was going to transport us to you, Bernoulli, but being that you mentioned it, I'll go right up to 1908, where apparently that was when the first rotometer was actually introduced. So basically the point is since the dawn of man, I'll say almost. We've been looking for ways to meter the flow of a liquid from one, point to the next. So I just thought I'd throw that out there. And, this is sometimes we think that, we're the creators of, and we certainly, modern technology, we're involved in that and pushing the envelope and moving things forward. But, people have been wanting to do this for a long, long time. Anyways, so, okay, let's go to the question at hand here. So I need a flow meter, guys. What's next? If somebody poses that question to you, where do we go from there?
Well, I really like the way you started off, Scott, with the example from Egypt, because I think that kind of hits the crux of what this conversation really is about. And it's less about the technology or the bits and bytes, and it's really starting with, what's important? What am I trying to measure? Why am I trying to measure it? And why is this flow value important? And so, Morgan, maybe let's start at the beginning. When you get thrown into an application and you're said, I need to find a flow meter, how do you break it down?
Well, I think the first thing you've got to think about is why am I trying to measure this flow? Why do I need to measure that stream? The obvious first question is I want to know how much is flowing, right? And it may be that you've got a custody transfer application that you really need to know how much is flowing in that pipe or over a weir or whatever it is, because the money is going to change hands on how that flow is measuring. So that's sort of your first one is that I need to know how much is flowing. But it's not the only case, right? There are times when you're measuring flow for process control reasons, but it's not a custody transfer application. So I don't necessarily need to have all of the same accuracy level that I need on a custody transfer application, but I need to have it be repeatable and reliable. Yeah. And then there's even less required accuracy when you start saying that I'm measuring something for process control reasons, but it's more that I'm using it to smooth out some other measurement. Like when you've got a level reset by flow where you're trying to say, well, I'm really trying to control a level, but I want to make it not change so fast, right? To upset the other parts of the plant. So the first thing is, what am I trying to do? Every process engineer who's ever tried to mass balance an operating plant, and I started doing this way back at the very beginning of my career, and then I've had to do it numerous times over the last 25 years. And everybody would love to have accurate meters on every stream in every plant so that you could measure exactly what's going through that heat exchanger or exactly what the flow through that pump is. But it's not a realistic ask, right?
Nobody's chasing that unicorn.
Well, you're chasing that unicorn, and nobody wants to spend that kind of money to get accurate measurements on every stream.
Yeah.
And because there's no cost benefit to it. The idea that some guy's going to come along 25 years from now and want to know what the flow is in that pipe isn't a justification to go spend a pile of money on measuring what's going on in that pipe, right?
And I think you hit something really key there. It comes down to a lot of practicality. And when I start looking at flow and flow throughout a plant, that's a perfect way to dive into it. It's a lot like that wooden board with pegs. You've got, not triangles, squares, and circles. You've got 50 different shapes. And really it's finding that meter, does the technology fit? Does the price point fit? Does my accuracy, my range? There's all these variables that really come into play. And so it's important to understand what works to make that pegboard complete, make that plant fit.
And there's also the trade-offs that you have to take with some of the selections that you might make, right? So if I take an example of that if I go back to the anybody who's been in this business a long time, or if you've spent time in an old plant that's 40, 50, 60 years old, there was a lot of plants that were built where everything was an orifice plate, right? You might have a rotometer on some really small stuff, but everything was an orifice plate, or very close to everything was an orifice plate. And then as people figured out that sometimes orifice plates are not the best option, they started with other types of meters that got used in different applications, whether they be turbines or vortex or whatever that is. But you didn't always understand what the consequences were of making that change, right? I mean, the classic example we've all run into is the plant that goes and puts a vortex meter in place of a orifice plate, but didn't recognize the low cutoff problem that the vortex meters have because they're so velocity dependent. And if you didn't shrink the line size or something like that, now your meters range got a whole lot smaller than it had been under the orifice plate. It might be more accurate over that very narrow range, but it's not as useful to you.
And you know, Morgan, I really like that example because as soon as we start diving into flowmeter, there's two big things that come into play. And one is the rangeability, you know. As I'm looking, do I really need to measure down to 0? Do I really need to measure up to 1,000? It's honing in, because as we go from technology to technology, orifice plate, vortex, great examples. Those are very different ranges we can measure.
Yep.
And what you hit on there is when you start looking at flow meters, it's very process driven. And where we see a lot of concern is really on that low end, really figuring out, when am I going to start running into physical, you know, the physics of it, limitations in my specific flow meter?
Well, and particularly if you're into a process control application, suddenly, I mean, if you've ever seen the horror of hitting the low cutoff on a vortex meter, when it's in a control application and your flow measurement went to 0 and your control system goes, open the valve, it's not a good thing.
No, definitely not.
Right? So you've got to look at those trade-offs, and you know, and also the trade-offs of what do I have to do to improve the rangeability of some of these flow meters, right? I mean, one of the classic examples is that, you know, when I started my career, sort of there was a rule of thumb of that when you did the hydraulics and you sized lines and how much pressure drop do I need to get through a system or to size a pump, you know, everybody allotted a couple pounds to get across a flow meter, because for an orifice plate, a permanent loss of a couple pounds was probably a reasonable thing to think about. But a couple pounds is not enough to get through a vortex meter with any sort of rangeability.
Yeah.
You know, and similarly, you're not going to get through a Coriolis meter on a couple of pounds of pressure drop and you know, get the performance you want out of that machine.
Yeah.
And the allowance that you say, okay, now when I do my calculations to size all this stuff around the flow meter, I have to take into account that there might be a penalty to choosing a different flow meter. Right. So when you look at the vortex meter is a perfect example. I mean, they're great if they're so sized correctly and selected in the right application. But if you have to say shrink the line size down for the meter run to get the vortex meter to have the rangeability you want, the pressure drop consequences might be pretty substantial.
Exactly.
Right. And if you're in a very high pressure application, it may not matter that much because you've increased the head on the pump by 1% or 2% or something, and that probably isn't a big deal. But in a low pressure application, it might be the end of the world.
And you know, I really like that, Morgan, because you hit on a very key point. The minute I think flow meter, I immediately think accurate sizing. They go hand in hand.
Oh.
You know, like we can get really good guideposts like, oh, I've got this gas run on a test separator. Typically, I'd go orifice plate. And it's easy to start there, but without a good, accurate sizing, especially when we start thinking compressibility of different fluids, gases versus liquids, that initial sizing, that getting it down, understanding your pressure drop, understanding velocities, I mean, that is critical to selecting the right meter.
Well, and even more than that, I think if you get into the exactly what are my fluid properties? I mean, some of the you know, and it goes again back to something I learned early on in my career. I don't know if you remember the root charts, those paper root charts, the round ones that had a pen drawing a line around them, and you'd integrate them to find out the flow. And but if you ever saw one that was a cavitating orifice plate, where you had a bubble point fluid going through it and cavitating across the meter, and it painted that chart so that it was useless. You got no measurement, right?
Yeah.
And I have seen that come back over and over again through my career of orifice plates and vortex meters put in applications where they're going to cavitate. Okay, did you understand the fluid you were going to have in that scenario? Did the physical placement even of where did you put the meter? You know, related to that is the example of, you know, you put a flow meter in and you check if you'd be cavitating across the meter, and then, you know, your layout guy decided that the meter could go above the liquid level in the source vessel.
And that's it right there. Right? You know, it's very easy to say, I'm going to look at my instrumentation. I'm going to just look at my flow meter in like a black box, and that's not the case. It's in a plant environment. It's downstream of a valve. It's, you know, maybe I've got reductions in pipe. Maybe I've got elbows or really crazy fluid properties that come into play. And so I find kind of the way you're hinting to there, we really need to take a holistic approach to when you put that flow meter in service.
Well, and
so guys, Sorry, I don't mean to interrupt, guys. So this just strikes me. You've talked about various different types of flow meters, and I'm just wondering, is there again for the guys who may not know that I'm trying to represent out here today, is there any sort of crossover? Like how does a person know that maybe he's just getting into the industry? When to go from one sort of technology to the next, because that's really what each type represents, right? It's sort of a different, technology used to measure the flow. Is there a crossover? Is there a one size fits all kind of a flow meter? And, what's kind of is there a price point there where it just maybe doesn't make sense, right? Depending on the application.
Maybe Scott, I'll dive in here, and I'm very curious to hear your perspective after, Morgan. So I think the one sentence I liked that you used there, Scott, is one size fits all, because that is the most false statement that we could possibly come up with. But it's really important to highlight. And when we look at flow meters, I think we have to leverage some of the tools that we have. So obviously being auditory, I can't show you anything, but we've got a great flow meter selection guide that kind of gives you a simple red, green, yellow. Red being don't use this here. This is going to cause lots of problems. To green's kind of a go. And where it comes into play, it's going to highlight some of those things that we talked about. Maybe gas measurement versus hydrocarbon versus steam, things like that. Show some rangeability. But really what it is, it's get you to a starting point. And I think what's more important is really have that upfront conversation with your vendor, and really with your advisors and your specialists to really talk about, here's what I'm looking for. Here's what I see typically used in industry. What's your feedback? What are your thoughts? Right. And start the conversation there. Like, how do you typically approach it, Morgan?
I agree with you 100%. It's have that conversation about what am I trying to do here? The selection guides are great because they tell you things like, no, don't try to buy a vortex meter in very large line sizes, right? Yeah. It's just nobody really builds them, and they've got all sorts of other issues when you get into big sizes. When you look at things like how much pressure drop do I really have available? Yeah. Am I down into the land of annubars and things like that on flare headers or ultrasonic meters or something like that? But also, again, look at what is the requirement that I have for accuracy versus repeatability and reliability. And similarly, it comes down to that layout question that you had, because some meters, when you start looking at them and saying, well, if I need to get accuracy out of an orifice plate, I'm going to need a meter run that has a fairly substantial straight run requirement, that has to fit into my plant. And you start looking at what does that look like in the real layout of the plant. And particularly if you said, oh, now I'm going to design my plant to fit into modules, and I'm going to modularize the plant. Can I fit this meter run in one module? Does the meter run define the module more so than anything else in the meter, in the module? That's a possibility, right? And so you need to think about those kinds of things when you're selecting that meter. Yeah. You sometimes see people want the one size fits all, or they want to write a spec that says by default use this meter unless you can otherwise justify it. And my recommendation is that is never going to work out for you. Yeah. Right?
It actually, so I know we're a kid-friendly podcast here, and we're not supposed to be swearing, but it brings me to a D word that comes to mind. And I've got a love-hate relationship with this D word, the data sheet. Now the data sheet has got all kinds of great information, but I think that's where it brings us right back to what you're saying, Morgan. A data sheet might say, hey, a vortex meter is perfect for this if I just follow the data sheet. But then when I start to go outside it, and now I start to learn a bit more. This is a flare application. I've got incredibly high turn down, very variable flow rates. All of a sudden, I'm starting to say my data sheet where a vortex might fit, maybe practically in looking at the application, I should be looking at a process ultrasonic now. And so I think that's where a data sheet coupled with good background information about what we're measuring, that's how you get a strong flow meter.
Yeah, absolutely. Because you're right, in looking at just the flow meter and not the application can get you in some trouble. And similarly, one of the things that I always thought was funny at the beginning of my career was being in a plant and seeing orifice plates installed in places where they didn't have big, long runs. Like they didn't put in long meter runs to improve the accuracy of the meter. And it wasn't until, in fact, years later when I realized that meter was never supposed to be accurate, right? That wasn't the point of that meter. That meter was a control meter,
Yeah.
right? It could be off as long as it was consistently wrong.
Yeah.
Right?
I like that word, consistently wrong,
Right.
because that in a crux is the difference between repeatability and accuracy.
Yes.
Yeah, as a control person, if I'm controlling and I'm always 20% off, but I'm 20% off consistently, I can program to that. I can make my pump work.
The operators in the plant will figure out how to make this thing work, and you can make the DCS control the plant even if that meter's wrong, as long as it's consistently wrong.
Yeah.
And
on the flip side, if it, like, I like when you talk custody transfer, as much as I'd love to be 20% wrong at the gas pump every time I fill up, I know it never works in my favor.
Right.
So now all of a sudden, my flow meter is way more important. And
Absolutely.
I need to size appropriately.
So that's where you get down to the, is this a custody to transfer application or a mass balance application, or is it a control application where the accuracy may not be as important as the repeatability is?
So that leads me to a question, guys. Like, how do you, when you move towards that custody transfer application, what type of meter are we talking about? Is there one that, it gives you the accuracy, the repeatability you need? Is there a specific type, or does it really depend on what you're actually trying to measure? So, like, is it a gas, a liquid, or what have you?
Oh, that's a good one.
Well, I think that, it depends on what are you trying to measure, right?
Yeah.
The meter you're going to use in a liquid application versus a gas application or a steam application are quite different.
Yep.
And again, there's can be a bit of an issue of scale of how big of a stream are you trying to measure. But, for a moderately sized stream that's a liquid, a Coriolis meter is going to give you probably the best accuracy and good repeatability, and it can measure the density of the fluid for you, right? So there's advantages to a Coriolis meter. The other thing I like about them is that they don't require you to sanitize a giant piece of your plant with a great big long meter run. But they do cost a little bit more, right? So there's that's the downside.
Well, and there's also something really important to think. Like, I think it's really easy to hear the words custody transfer and have a misunderstanding about what that means with respect to accuracy. And we've got great guidelines out there, like AER Directive 17, which your measurement specialists will be really strong on. But it starts looking at as less in terms of your individual components as more, hey, on this custody transfer line, I need to have a total accuracy of blah. And that's not just the flow meter. It is the flow meter. It is if I need pressure, temperature compensation. It is maybe I need a flow computer. And so really we need to start thinking about all these things and how they combine. And custody transfer can mean different things. Maybe it's internal to a company. That is different custody transfer than, let's say, I'm a midstream company tying into a pipeline.
Yeah, absolutely.
So guys, I've heard of and worked with like a multivariable transmitter in the past. Why would you say that's, you mentioned different compensations, measuring density, etc. From the sort of newbie's perspective, tell me why going with a multivariable would be better than perhaps, having different transmitters to take all those other measurements.
Well, that's a really good question, Scott. And I think kind of Morgan alluded to earlier, again, this is another one of those trade-offs. There's gains and losses. So one of the best I can think of is steam measurement. Steam measurement is one where we don't really deal with high-quality steam in our territory, especially when you look at what we're dealing. So when I say not high quality, there's a lot of liquid there. And so what we run into that's a big problem in measuring steam is impulse lines, or these big long lines that we let that steam go through so we can do the measurement. Those impulse lines, especially with our environment, very prone to fouling, plugging, freezing. And so one of the things that a multivariable transmitter or meter might help you get around is eliminating those impulse lines. It's all one body. You reduce leak points, things like that. So that's a great example of a trade-off in the positive side that you can get. But what are some of the negatives that you've seen, Morgan?
Well, one of the negatives of when you get into saying you're going to do pressure and temperature compensation, and those are separate transmitters, is if one of them starts to go bad, right, and you don't know that it's gone bad, or if somebody's done maintenance on it or changed it out. I've seen an example where somebody changed a temperature transmitter and put in a different range of transmitter, but didn't reconfigure what the DCS thought it was going to get.
Yeah.
Right? And it changes what the flow measurement is.
Right.
So that's one example of when that can happen. Steam measurement's another good one. It's another dangerous one where you look at things like, or even wet gas measurements, where you're running them through, and say you decide you're going to use an Orifice plate because it's a good fit for the system. Now I've got these leads to the DP cell, and do I run the risk that one of them gets full of liquid?
Yeah.
Right? And how do I make sure that's not happening?
Yeah.
Right? And those are the kinds of things you need to think about as you're selecting your meter, and selecting how am I going to lay the meter out to prevent that from happening, right? Because we've all seen the flow meter with the liquid filled leg that's causing it to be wrong, and now inconsistently wrong because that leg has got a different amount of liquid in it as the conditions changed.
So would there also be an impact to like your sort of total installed cost when it comes to picking, choosing one over the other, or is it kind of a wash, I guess, right?
Morgan, actually, I'm curious to hear. I'll give you one of the things I think about, but let's say with the same steam measurement, obviously, if you're removing impulse lines, operations, maintenance, installation, that goes down. It's one model, things like that. When you guys are procuring or looking at this, if you have to do, let's say, 3 separate measurements, flow transmitter, a pressure transmitter, temperature transmitter, that would be, 3 different data sheets, 3 procurement cycles. Would that come into play?
You might end up with 3 different data sheets. You might find a way not to do that, but you probably don't. You may end up in different procurement cycles because you're going to buy the temperature and pressure transmitters on a different timeline than the flow measurement device. The other thing that I think is interesting is the question of how are you wiring these things, right?
That's a good point.
Because
DCS space isn't cheap.
Well, not just that, but if I'm using a multivariable controller, and depending on how I'm going to wire that thing, it might be one cable. Right? But if I've got 3 separate transmitters, I might now have 3 cables.
Right.
And that cable cost, depending on how far back I have to run those cables to whatever method I'm going to use, and I'm by no means an expert in the different ways to wire these things, other than I get baffled by folks who are. The question becomes you might find yourself spending an awful lot of money on cabling. To install 3 separate transmitters, and you've got to put that into the equation of making those decisions.
Right.
And then
what about
I'll do one last one, Scott. There's also there are some technical advantages, even if we go beyond and look at things like diagnostics and features, and that steam is a perfect one. So if we look at a vortex meter, one of the things, steam is a very defined fluid, and we have defined steam tables such that if you've got your actual volumetric flow and a snapshot of your pressure or temperature, you can directly translate that to mass flow utilizing some of these tables. So if we look at Vortex technology, they now have these tables built into that meter. So by employing this multivariable transmitter, I've simplified my programming, my interfacing to get the units that matter, kilograms per hour.
Assuming you've got dry steam.
Assuming dry steam, yes. That's a good point. Assuming dry steam.
So my next question I was going to ask, we sort of touched on installation costs. What about from a maintenance perspective, I guess, right? I mean, I think about if I have to look after 3 different transmitters as opposed to 1, but the truth of it is I don't know all the complexities that would go into, maybe one, the multivariable is harder to maintain or look after than the other. I don't know. I'm asking the experts here. Because certainly there is cost from the operator, right, to not only have the 3 installed, but then maintain them going forward as well, right? So thoughts on that?
You hit a really good point there, because now we start talking about inventory, spares, things like that, because now you can start reducing that. You can know that, if I've got a certain application, I can just grab this off the shelf and I know I can drop it in place. Maybe I'm not running into these rangeability issues. And then I think another thing that really hits on, Scott, is understanding more than just the meter. Once that meter is installed, how am I connecting to it? Do I have really easy software on a laptop? Do I have a handheld? Am I HART compatible? And more importantly, when I connect up, does that show me everything I need? And where that becomes really important, let's take a Coriolis, for example. when I go in and I hook up using ProLink or a handheld and being a multivariable device, I need to see my flows, my instantaneous. I need to see my totals. I need to see any pressure, temperature, water, whatever happens to be coming into that meter. And I ideally want to make it so that it's one piece of software, one tool. Otherwise, it's pretty tough if I have to learn one thing for my flow, one thing for my pressure, one thing for my temperature.
Another aspect there is, and by no means am I an expert in maintenance or maintenance costs, but when you get into trading off those comparisons, one of the issues that comes up is that if I've got separate temperature and pressure transmitters, then I probably have a separate thermal well, and I have separate isolation valves on a pressure transmitter that are separate from the multivariate device the option, or if the flow meter. And so now I have to worry about, do I have double block and bleed on that pressure transmitter, or don't I? Should I have put it there? Would the mindset of the way the plant was built 20 years ago versus the way we would build a plant today change whether we would put double block and bleed on that type of thing?
And I love that example because what you've highlighted there is something crucial. It's thinking about once my meter's in place, obviously when we think of proving or making sure a meter is accurate, do I need to isolate my line and shut down my process? Or can I verify things with that meter running? And so thinking like smart meter verification, where you don't have to interrupt your process to verify. All these are things that are kind of can be difficult to convey on a data sheet, but become really important when we start talking installations, operations, and maintenance, because as we know, shutting down a process is an expensive procedure.
Well, and that's brings up a good point about, that touches on a much bigger picture issue, which is how is this capital project being executed? Yeah. Right? Because the contract structures that exist and the who's making the decisions may come into that, right? Because if you've got the designer who's designing the plant doing this on a fixed price contract and they have no requirement to look at what the life cycle cost is, they're going to buy the cheap one. Yeah. Right? Now, most people are smart enough not to write a contract that way. Yeah. But it's one of those things you have to take into consideration that if I want this to be, nicely maintainable and I want to worry about those life cycle costs, let's not get too focused on the capital cost of it right up front, right? And I think that brings us back around to the question of look at the big picture. Yes. Because some of these systems, when you start looking at what's the cost of that flow measurement device versus the installed cost of the flow measurement device. Right. Yes. It turns out the flow measurement device is not the bigger chunk of that cost, right? If I've got big, long flow meter runs, if I have to have separate proving taps, if I have to have, a bypass around the flow meter for a proving station, and now this is going to take up a bunch of space in a structural steel module, and oh God forbid somebody wants a building on it. Yeah. Suddenly the cost of the flow meter is not the biggest thing that should be the thing that drives the decision making. And
it's that sticker shock, right? Because I love that you keep bringing up Orifice Plates, because there's a great one that has this really perceived cheap cost to it, but that's because you're just looking at a plate. Once you start, like you said, I've got some flanges, I've got to tap them, I've got to worry about piping, maybe I need a flow conditioner, I need my transmitter that can read this DP, I need to bring that back, and there's all these things and that keep building.
Well, and you get into the Orifice plate looks really cheap. Yeah. But what if my meter run is 50 feet long? Yeah. Right. That's and that can be a big deal. Yeah. Right. And it layers onto all sorts of things like, I've got a 30-meter meter run in a high temperature, high pressure application. That is a really rigid piece of pipe, and now the pipe stress around that starts to become a problem.
And the worst part, we haven't even talked about what happens when my process changes. Because, there could be we need to think years down the road. And one of the things that, when we talk rangeability, a range of an Orifice plate is only so much. And so, when we start thinking about future proofing, that adds a whole nother layer into the discussion.
Yeah, right. I mean, I've heard it said though that I can always just change the plate. I'll just put a bigger plate. I'll just put a bigger orifice in. Well, there's a limit to that. I'll change the DP cell, so I'm measuring. I'll double the DP range on the measurement. But again, then your accuracy starts to go away, and all of that. So absolutely, it's a big question that you've got to think about ahead of time. Oh yeah. And it comes back to that problem of how much is my process going to change? Another classic example that I saw a couple of years ago was, what if the composition of the gas that's going through the meter is not what you thought it was going to be? And what if it's not even something you thought you should measure?
Right.
Right.
So hey guys, let's get back to that great discussion so far, but just a quick break for a commercial here, if you will. So stand by as I pay the bills, so to speak. So just wanted to thank Spartan Controls, local impact partner for Emerson Automation Solutions, selling and supporting industry-leading brands such as Rosemount, Fisher Valves, and the Delta V distributed control systems. We also represent a number of complementary brands such as Detronics, fire and gas detection systems, Yaskawa variable frequency drives, as well as Hyundai Motors. Not only that, but we have in-house expertise and solutions for combustion management, as well as compression and many others. Please go to spartancontrols.com to see all we offer. Thanks very much, guys. So let's take that from where we were there, Morgan. You had mentioned, that sometimes what you were expecting to measure wasn't necessarily what you were actually measuring. Can you elaborate a little bit more on that?
Yeah. So the case of any volumetric flow meter, whether it be an orifice plate or a vortex or an ultrasonic, they're just measuring volumetric flow. And therefore, to convert that into a measurement that we're going to use for whether it be control or custody transfer, I need to convert that into some standard volumetric measurement, or God forbid a mass flow, or equivalent mass flow, or whatever that happens to be. But the composition becomes an important part of that. When we talk about pressure and temperature correction, well, okay, but what's the composition? Because that may change. We all know PV equals RT, but what about Z? Right? And the compressibility of that fluid. What's the molecular weight in that equation? Right? That all matters. So when you start looking at how am I doing the calculations, and what measurement am I using? How often am I updating the composition information?
And, I really like that conversation, because when I look at a plant, obviously with compressible fluids, let's look at gas. If I change my pressure and temperature, that volume can swing significantly. And the way I like to think about it, across a plant, depending on where I'm measuring my volume, I'm measuring in yen here, US dollars here, Canadian dollars here. And when I talk about this pressure temperature compensation and bringing it back to standard, what I'm saying is, across the plant, I want everything to come back to Canadian dollars.
Right.
So now that I can sit there in my plant, I have a really good understanding of how things are actually performing.
Absolutely. And composition in most cases isn't going to have as big an impact as pressure and temperature on how accurate that measurement is, but sometimes it does. And recognizing that, do I see a cycle in the composition of a stream that happens day to night, for example, or summer to winter, or is it a mode of operation that I'm running the plant in a different operating mode? An example I've seen in a refinery was, in a hydrotreater, where depending on exactly what blend of feed I was running, the composition of the recycle gas going around and around in the loop ended up being quite a bit different. And when it's supposed to be mostly hydrogen, changing that changes the molecular weight a lot. The difference between a molecular weight of 4 and a molecular weight of 6 is a big difference when you're doing a flow measurement. So that's you may not see that in a natural gas application where it's changed from 17 to 18. Right? That's not as big a deal as something that would change from 4 to 6, but it's one of those things you have to think about of how am I doing the math.
And that's a great example, because molecular weight, if we were to take that sizing and take 2 different snapshots, all of a sudden our rangeability really matters, because things are going to swing significantly.
Absolutely. Yeah. And you may find that the meter's rangeability, you fall off the end.
Exactly.
Right? And then you really don't know where you're running.
Yeah.
And So that's a key thing, because the other problem is that you can't measure composition all the time, right? Most times you're going to measure composition intermittently and update the calculation. And in my experience, that's one of the biggest reasons why it's hard to mass balance a plant. Is it's not so much the accuracy of the meters themselves; it's how often do I actually have composition information.
Yeah, that's an excellent statement.
So that's a good segue, guys, because great talk so far on the different types of flow meters, different applications, etc. So even in the title of our episode here is, I need a flow meter. What's next? But how do let's say someone comes to you and it's like, well, I have a problem, right? Can a flow meter actually help me fix this problem? And Morgan, you actually the other week had a great example where, you went in, to sort of, I think it was to install some flow meters. Well, you tell the story. Do you recall the story that I'm
Oh,
actually
good. He's
talking
leaving you
about?
with your thunder. I thought it was going right away.
Was this the air story?
Is that when you're
yes,
the air
okay.
story?
That's the one. Yeah.
So and this happened many years ago, in a plant that shall remain nameless. But it was an older plant, and there was a desire to improve the instrument air system in the plant, and modernize it, because the plant had a bunch of older machines, older compressors, and they needed to understand, well, how big a new air compressor do I need to buy? So the decision was to go put flow meters all over the plant, on the discharge of each air compressor, and measure how much compressed air the plant was consuming. And they did it both on instantaneous measurements and gathering all the data, and then totalizing it to figure out on average, how much air do they need to come up with a size for an air compressor. They just slapped Orifice plates on the back of every compressor. And you can imagine that sticking an Orifice plate on the back of a recip air compressor with no meter run, how accurate is that measurement really going to be? But they did it, and they came up with a number and bought new air compressors and installed these brand new air compressors, and they were good screw compressors. And then they started the plant back up, and discovered they didn't need all those air compressors. And the reason is that during the turnaround, they had left an air compressor on to keep the system alive through the turnaround, and somebody walked around looking for leaks, or more importantly, listening for leaks, and found some doozies that they fixed. Right. And so it comes down to a question of, did you know what you were looking for? When you put those measurements in, did you understand that maybe not all the air you were compressing was getting to where it was going? Now, instrument air is a pretty innocuous thing to have leaking out of a system. But there was obviously a cost to that, and right. it led to some maybe sub-ideal decision making on how big of a compressor should I buy. But it really comes down to, did you even know what question you were trying to ask? And I come back to what we talked about at the beginning.
I'm sorry, were you asking me that? Is that the question you're asking?
It was kind of a rhetorical question. It was a rhetorical question. But it brings us back to that thing I brought up at the beginning, which is what is the purpose of the flow measurement?
Yeah.
If it's a control application, do I need all that accuracy, or do I just need repeatability? Right. Is it a custody transfer? Is it a custody transfer or custody transfer-like application inside an organization, or is it actually something where real money is going to change hands?
Exactly.
Right? Or there's a regulatory requirement. One of the classic examples is the MARP requirements that the AER has on mass balancing a plant. And it's kind of entertaining, if you've never done it, to go look at some of the reports that the operating companies put forward to the AER about their annual operations, and some of the correction factors they have to put into their MARP reports, and you think, ooh, that's a little scary that mass balance is out by that much. But in my experience, those aren't abnormal errors in a mass balance around a plant. If you can take a mass balance around a plant and get within 2%, you are a hero.
Oh yeah.
Right?
Yeah.
If you're within 5%, you're doing well. Yeah. And it comes down to that it's not just meters, but meters play a big part in that. But and I think one of the things that people fall into the trap of is trying to find a meter that does it all, and sitting there and worrying about the accuracy of a flow meter that's being used in a control application that is primarily a control application.
Exactly.
Right? And then you get into this agony of, well, I need this great big meter run, or I have to buy a expensive meter because I don't have space for the meter run. But do I need that accuracy or not? Because if I don't need the accuracy, don't pay for it. Right?
Yeah.
Exactly.
And that's a really great point, because I even loved how you touched on the environmental side too, because obviously metering, we're seeing it more and more as we start to move towards, let's stop pumping gas into the environment. Let's take away those greenhouse gases.
Yeah.
How do we attack that? How do we, because we know it's a tricky measurement. Typically it's low flow, low pressure.
Absolutely.
We need an accurate solution that can help with our carbon credits and things like that.
Yeah, I mean, flare measurements are a really
That's a
good
great
example.
one, yeah.
Flare measurement, vapor recovery units, you know, what's coming off of tank farms and all of that kind of stuff. Those are hard applications because now it's, no, I need accuracy and I need repeatability, but they're not applications that are easy because they're at difficult conditions.
Yeah.
You know, it's. I've always said that, you know, measuring things at high pressure is easy.
Yeah.
Measuring things at low pressure
Yeah.
is really hard,
Very tough.
right?
Yeah.
Excellent. Well, I think looking at the time here, guys, we're getting to, or at least close to the end of our episode here. What I'd like to say is hopefully that any listener or viewer, was able to, gain some knowledge here around flow meters and understand why one technology might be beneficial over the other. We had a great discussion around different applications and even sort of, I want to say, how, installing some flow meters led to a better understanding overall of an application around the instrument air that Morgan had covered as well. I'd like to thank Dane, of course, as well as Morgan Rodwell for joining us today and taking the time to be a participant in our podcast. Guys, it's been a pleasure. Hopefully we do manage to gain a solid viewer or listenership here, and we can do many more of these. So hopefully folks out there can join us again. Our next topic will be Delta V modernization with Gabe Fantino. Any closing remarks, guys, before we cap it off?
I'd just like to thank you guys for having me on this podcast and to try out the maiden voyage, as it were, and I hope people got some value out of this.
Right on.
I'm sure they have. Yeah. Thanks, guys. Very much appreciated.